Hey, thank you for checking out this video on the alpha halogenation of carbonyl compounds. The one page of notes that we skipped during class, again, we won't require you to, we won't ask you about this on my exam, but this kind of material might be found on like an ACS exam or MCAT or what have you that you might take in the future. So it is usually part of the OChem curriculum that we just didn't have time for. The main thing I want you to get out of this is the contrast between the acid catalyzed reaction and base catalyzed reaction. And we've made that contrast during class before, but going through this particular type of reaction, the alpha halogenation might help you with that even further. So one of the key ideas is that the results will be different between acidic and a basic condition. The first reaction here, I just want you to notice that it's an acidic condition because of the solvent, that's acetic acid or ethanoic acid, and the product is monohalogenated product like the one you see here. Okay. And so why would that be the case? So here I've taken the liberty to draw the mechanism, most of it already. The first thing that could happen with the ketone, really the only thing that could happen with the ketone is acid-base chemistry, where the ketone carbonyl could pick up this rather acidic proton. Remember, that is a proton of a carboxylic acid, so it's fairly acidic. So once it gets protonated, and here, it could form two different enols, either this enol or that enol, right? Now, I want you to think about the Zaitsev rule. The bottom one would be the more stable enol, and that's the preferred enol. You might think, well, gee, isn't that confusing here, because we're saying that both of these processes to both enols can happen. What I'm trying to show you here is that they can both happen. It's just that this enol is the more preferred. So you would accumulate this Zaitsev enol more so than the other one. And so for that reason, it's this Zaitsev more stable enol that reacts with electrophilic bromine. And remember that there's a fair amount of partial negative charge at this alpha carbon because of the resonance. And so it's that alpha nucleophilic carbon that attacks bromine, which ends up being this brominated ketone. And so for that reason, right, like this becomes the product. Now, another key point about the acid catalyzed reaction is that now that this has a halogen on it, there's now less electron density on this carbonyl. And so even when it becomes enol, it's just not going to be nucleophilic enough to go through another round of reaction. So the reaction stops with mono halogenation, and that is it. As opposed to when we have a basic condition like this, all of the alpha protons can be replaced by halogens. In other words, in this particular instance, I want you to notice how there's two halogens on the alpha carbon, and so then there could be two bromines for the product. Okay. Now, how would this work? Well, first, because we're under basic condition, instead of enol, we expect to see enolate. Okay, like so. And once you form an enolate, remember there's a really good amount of partial negative charge there. So it reacts as a strong nucleophile. This is a strong nucleophile. So we can get the first halogenation happen. This is basically an irreversible step. So we'll just draw it like that. Now, and then you might think, well, so don't you end up in the same place? The only difference is, even though bromine or halogen is electron withdrawing, that actually stabilizes the enolate, you see. So when the hydroxide takes the proton off to make the enolate, this is a negatively charged species that is stabilized by the electron withdrawing bromide. But because it is negatively charged, this is a strong enough nucleophile. Even though there's a bit of electron density suction towards bromine, right, even so there's a full negative charge, as opposed to this enol, which doesn't even have a full negative charge. And so for that reason, this is strong enough to react with yet another bromine molecule. So technically we should have said there needs to be excess bromine here for this to be true. But once that happens, that'll be the product. So that's the alpha halogenation.